This is the detailed diagram. So we heat it, use the steam. It's somewhat high temperature, 200, 300 Celsius. So we have burner, furnace, everything. No detail, not just so you know that it looks just like this. So we heat it several stages. Okay, just that. So it has these two reactions happen inside, and the byproduct is this yellow thing, pyramid. This yellow thing. Okay, that's the product. Yes, question.
So it's wet, sour gas going in, since it's coming after the chemical.
Because if you look at this thing, it's one of the product already. So eventually, this thing that we get, it will be wet anyway. See this yellow thing, sulfur, it come out with H2O. Is it? So you can see that we connect it directly. We don't do any water removal before Klaus process. Klaus process sit next to amine unit. The acid gas, of course, it's wet. It go to the Klaus process. It's fine that way. Okay, that's the Klaus process for the case where we have high concentration. H2S is more than 50% of the stream. What if we have low content? We use another process called low cat. Low cat is kind of the process licensed by American. It have reaction with iron, and eventually we get elemental sulfur. So it's different kind of reaction. Okay, and it's for the less content. So we have gas coming in, and it go to the solution of this solution, and then we have solid to the bottom. Of course, there are more in this, but basically low cat process is for low H2S content, and it produces elemental sulfur. Good. Okay, let's do next. Okay, who is next? Levi. Physical or chemical solvent require more partial pressure of the feed gas stream for acid gas cleaning purpose. Correct. Okay. Basma. Ion sponge solid base is a process with the main purpose to remove water or H2S. Correct. Sulfur treat. Okay, next is Kai, right? What's your name? Kai what? Harrington. Okay, Kai. Sulfur treat process for H2S removal is what? Solid base, chemical solvent, physical solvent process. Okay, next. Who's next to you? What's your name?
Landon?
Landon?
Yeah. Solid bed.
Solid bed, correct. Okay, next one. Jared? Regeneration of chemical solvent require more energy than that of physical solvent. True or false?
True.
Correct. Where are they? They just gone? No one sit next to you? Okay. Another kind. Okay. Membrane for H2S and CO2 removal operate by filtration technique where large molecule cannot pass through the membrane pore. True or false? False. Membrane, the part that do the selection doesn't have any hole. Okay? Very good. Selexol is the who's Clara? Okay. Selexol is the physical or chemical solvent process? What?
Physical.
Correct. One of the products from MEA, DEA, MDA process is
H2S.
sulfur element or H2S rich gas? H2S rich gas? Okay. The product from Klaus process, acid gas treating is, the product is what? What's it? Alex again? Okay, what is the product?
Sulfur element.
Sulfur element or elemental sulfur. Low cat or Klaus process require higher partial pressure of acid gas. What's the name? What's the name?
Scott.
Scott. Which one require higher partial pressure? Klaus process. Correct. Primary amine has chemical structure of that, true or false. Next is Madina. False? Correct. So for primary amine, we have just one R, right? So this one is secondary amine. Sweet gas living amine unit is typically dry or wet? Simon? Wet. Correct. Okay. Now I replace it with 1, 2, 3, 4, 5. You know how to do it? Put all this number in. Afshin, can you do it? What's number 1? Pardon me? Number 1 is what? Correct. Number 2? Afshin, sweet gas. Number 3? Rich amine. Number 4? Lean amine. Number 5? Acid gas. Are you ready, Afshin? Very lightly. What else can I ask you? I can ask you either this or dehydration. The gas dehydration process. So we remove all the gas, right? We remove all the gas, or not all the gas. Remove all the acid part. Now there's still some water in it. Then we have to remove water to make it very dry. Or we can use molecular sieve again to make it very, very dry or something before it goes to cryogenic process. Okay? Okay. How do we remove water? We can use separator. Separator can remove big droplet water. But for small droplet water, we use gas dehydration unit. Okay? Such as glycol dehydration unit. Or we can do calcium chloride batch treating if we have very small volume. Okay, so we have corrosive brine as a byproduct. If we have calcium chloride, it can catch some moisture in it, but it's not typically used. Okay, because this is for very small amount. Or we can do adsorption on the solid. Use a molecular sieve to make it bone dry. Very, very dry, like no water at all before it goes to the cryogenic plant. Okay, this is absorption on solid. So it's dehydration before the cryogenic recovery of natural gas, okay, and helium. Or we can do absorption. Oh, what's this? This is the difference between absorption with A and B and adsorption A and D. Adsorption with D, fluid molecule adhere to the surface, okay, to the surface of liquid or solid. So adsorb with D, it just go to the surface. Absorption with B, it go to the bulk phase. That's a difference. Okay. So if we have a lot of water, but cannot be catched by separator, we use glycol dehydration unit. Okay. Separator remove free water layer, yet 25 to 120 pounds per million standard cubic foot of water remain. And we need to, just 7, right? We cannot live with 25 pounds per million standard cubic foot per day. It should be lower than 7 pounds as per the gas contract. So water-free glycol, quite pure, is used to absorb water vapor from gas stream. The commonly used glycol is triethylene glycol, TEG, is the commonly used one. You should know this. Okay? You should know this one, TEG. Contact tower is used to increase the surface and allow TEG water absorption to reach equilibrium. Lean glycol and gas stream flow countercurrently in the tray or the packer contactor. Glycol absorb water at low temperature and release water at high temperature. So the way it works is the same, similar to amine contact tower. But you just have to change the word lean amine to lean glycol. Just that. The rest is the same. So what happened is lean glycol come from the top. Okay. Gas go from the bottom. The product on the bottom is rich glycol. Rich glycol means glycol with water. Glycol with water go into the regenerator. So we heat it up and then we have water vapor coming out. Okay. Good. Water vapor coming out and lean glycol go back to the top part. So it's very similar. Okay, glycol unit. We can have this generator, or we can have two towers. Glycol regenerator, glycol contactor. Glycol contactor is the same as absorber and regenerator. So it works similarly to amine unit. So it's have heat exchanger, glycol pump, something. And the product that we get is dry gas. It may have, it won't be bone dry yet after glycol dehydration unit, but it's dry enough, less than 7 pounds per million standard cubic foot. If we want it to be very, very dry, what do we do? Very, very dry molecular sieve. If we want it to be very, very dry, we flow through this kind of ball, many of them. So this thing will catch all the water, right, and make it very, very dry. Molecular sieve. Do you know how to spell molecular sieve? No need to be able to do it now, but maybe Thursday you will be able to do it, right? Okay, glycol dehydration. Property we can. It's the reason that we use glycol because it has high efficiency. Is cheap or less expensive. Is economically feasible for the regeneration process to happen. Non-corrosive. It's not toxic. It's just same thing as an antifreeze that you use. Okay, but this time there's just no water. No operational problem when used with high concentration. No interaction with hydrocarbon portion of gas. No common contamination by acid gas. Okay. Glycol comes closest in satisfying this criteria. So therefore they use glycol for dehydration. Okay, very common. We have several of them use TEG. It's the most common. The reason behind it, read by yourself. Okay. And this is the operating temperature. That's it. Question. You read it. So what do I say when you read it? It may not be in the exam, but I would expect you to put it on your report. Okay? So when I say go read it, put it on your report. If you copy and paste as a picture, that's a low quality. Okay? I want you to type so that I make sure that you know it, so that I know that you read all these. Okay? So this part, you just read it. Okay? TEG, dehydration operating condition. Go read this, type it on the report. Okay. Very good. I think now we can do this. What type of glycol that is typically used in glycol dehydration unit? Triethylene glycol, TEG. Is it triethylene glycol? Yes, triethylene glycol. What is the main method for regenerating glycol in glycol dehydration unit? Increase temperature, right? Afshin, Karim, do you increase temperature to regenerate it? What is it? Yes! We heat it up, okay, to regenerate it. Glycol dehydration works by absorption or adsorption. AD or AB? Absorption, right? Maybe I skipped that. Did I skip that? No. So it works by absorption with B. Okay. Absorb water in the bulk phase at low temperature. Last one, lean glycol enter the glycol contact tower from the top or the bottom? Emma. Is that Emma? No, Benedict. Top or bottom? Top. And you can do all this, right? 1, 2, 3, 4. Mobile. What is number 1? Number 1, what do you call that? Wet gas. Mobile number 2. In the exam, you may not have choice, okay? But right now you have choice. Select it. Number 2 is what? Is that number 2?
Yes,
Less scrapper. Number 3.
Absorber.
You don't have absorber. Yes, absorber is correct. Another word, we can say glycol contactor. Number 4.
Dry gas.
Dry gas. In the exam, there's no one to circle this for you. You know that, right? Number 5 is what? Mobile. Oh, number 5 on the bottom. Number 5 on the bottom. Mobile. Number 5 on the bottom. Rich. Glycol. Okay, correct. Number 5 on the top. Lean glycol or water vapor? There are 2 choices. Are you ready? The exam is coming. Is it number 5 on the top is lean glycol or water vapor? Lean glycol. And number 7 will be water vapor. Of course, number 6 we call it regenerator. Mobile, are you ready? Every time that you make it wrong, there's a penalty. You know that, right?
Yes, sir.
For true or false or fill in the blank, those memorization things, you got to be able to do this. Additional question. Do it at home. Okay. What is the process used to remove nitrogen? We didn't cover it, but it's cryogenic process. Because you know that select all, no, remove H2S. TG absorption, remove water. Ion sponge, remove H2S. Molecular sieve, remove H2S. Or some kind of acid. So it has to be cryogenic process. Cryogenic process, remove nitrogen. It make it very cold and nitrogen come out. Okay. Between gas dehydration and gas sweetening, which process you prefer to be done first? Mobile?
What's up?
What's that? Gas dehydration or gas sweetening? Which one should be done first? Mobile.
The dehydration first.
Dehydration process. Wrong. Sweet? Yes, should be done first. We remove acid first. Okay, behind you, what's your name?
Olivia.
What?
Olivia.
Olivia. Okay. Olivia. Number 4. Water content that is generally acceptable by gas pipeline in Texas is how many per MMS CF no D. Okay, how many pound? 7 pound per MMS CF. Yes.
Will you go back to the glycol thing real quick?
Okay, we'll do that later. Number 5. Which unit is typically for making a bone dry gas for cryogenic process? Emma, which process do we use to make it bone dry?
Dehydration.
Molecular sieve? Did you say molecular sieve?
Yes, I did.
Molecular sieve. Molecular sieve dehydration is what? Absorption or absorption process? D or B? D, right? Absorption process. Picture A, where's this one? Picture A, John, what's picture A?
Amine unit?
Amine unit. Is it? I don't remember. Picture B is what? Oh, that's it, picture B. Picture A is select salt. Picture B, I don't remember. What do you say, John?
Amine unit?
Amine unit?
Yeah.
We'll check that. Picture C is, John? What is picture C?
Molecular sieve.
Molecular C.
Yeah.
Next to John, what's your name?
Hayden.
Ed,
Hayden.
headed.
Yeah.
What is picture D?
The membrane.
Membrane process. Okay, picture B. Let's go back. Is that what was it? Oh, no. Picture B is amine unit. Yes, it's amine unit. Okay, let's go back to what do you want to go back to? Molecular sieve is adsorption process because it's attached on the surface, not on the bulk phase. Okay, that's the molecular sieve. Did I say somewhere adsorption? No, but okay. Glycol? Yes, glycol unit. Is it this one? Next one. Regenerator is to heat it up.
Right, we said that entire, like, right?
This whole thing, we use it to regenerate the rich glycol, to make it really glycol. We call it regenerator. Sometimes you may have it as that glycol regenerator. Good? Okay. Now you finish everything that you cover in the exam. Okay. We have 20 more minutes. Let's do this quiz together. Okay. Did you write your name? So, okay. This is about modified flow that we didn't cover, and we shall go through it together. In this case, consider slug flow in an inclined pipe. The figure shows the solid particle being scooped by the slug. The solid particle travels with the slug and eventually is checked back into the liquid film behind the slug. The figure shows four sequences. A. Initially, the particle is just ahead of the slug. So we have solid particle over there, ahead of the slug. Okay. And B, the solid particle is scooped by the slug and travel through the slug. So solid particle get picked up by the slug. So it's scooped by the slug. And C, particle is checked back into the trailing film and travel through it. So particle go into this one, move through, slug move, and it moves together with slug. And particle check back at the back. Okay. And then it go through the film and next slug hit. This thing, we assume there's no slip between solid phase and liquid phase. What this should telling you is, for slug flow happen, the interface move faster than the liquid phase itself. Liquid that is inside the slug body will travel at the same speed as this solid particle, I assume, okay? Will travel at the same, actually there will be some lag, but what I'm saying is, the front, this part, move faster than that dot, okay? The interface move faster than the liquid inside, okay? So when the interface move this much, the solid particle move not that much, okay? So when the interface go from there to there, particle move just from there to there. So it moves slower than the slug bodies, than the interface itself. The liquid inside the slug body moves slower. Okay, you get the point? And then liquid inside the film move slower than this interface. So you may think that this interface move together. So liquid inside the film move even slower. So eventually, even though the solid particle move forward a little bit, but the front of the next slug is moved so quick. So this thing move ahead a little bit and it hit with the front of the next slug. From this diagram, you should know that the interface moves fastest. Liquid in the liquid slug body moves slower than the interface itself. Liquid inside the film moves slower than the interface itself. So the interface moves very quick. It moves at the speed of VTB. We call it travel at the speed of, let me zoom in a little bit more. VTB, translational velocity or speed of the Taylor bubble. So the Taylor bubble moves very quick. The interface moves at that speed. The liquid film inside travel at the speed of VLTB. So VL is velocity of liquid. TB means in the Taylor bubble. So liquid inside the film moves slower. Okay. Gas in the Taylor bubble travel at the speed of VGTB, V gas in Taylor bubble. So gas in the Taylor bubble moves slower than the interface velocity. Okay. And we have, I think there should be 2 more copies left. First extra. Can I have the extra? How many extra do you have?
I just have one.
You just have one. Who else have another one? Oh, Danny has another one. Yeah, let him have it. So everyone come to class today. Do you know who missed the class? No, no one missed. You can give it to me. Okay. So liquid gas mixture inside the slug body travel at the speed of Vs, mixture velocity, and mixture velocity is just VSL plus VSG. By now, everything that we do here is just the explanation about why this, how the fluid element inside the slug body moves slower. So this is not about gas treating. Okay, we go back to the slug flow. Okay, let's do this. The time required for the slug body front interface to travel at length LS is how much? How much is the time required? So next to Hayden, right?
Yeah.
What's your name?
Right.
Brian? How much is the time required for the front to travel at LS meter?
Depends on the time.
So we length divided by velocity. And we know that the velocity is VTB and the length is LS. So the answer will be LS over VTB. Would you like to write it down? So this has to be LS over VTB. Okay. So the front move somewhat fast, right? So for it to move at LS is the length of the slug body. LF is the length of the film. Okay. Question 2. Demila, the particle inside the slug body travel at the speed slower or faster than the slug body front interface?
Slower.
Slower. Correct. Okay. Next, direct. Question 3. As the slug body front interface travel by LS, the particle inside the slug body travel by how many meters? Let me give you the hint. Okay. If we want to know how much the particle travel, you see this particle travel. So when the front move by LS distance, it takes how much time? Yes. So the amount of time that the front take is LS over VTB. The solid particle inside the slug move at what speed? Vs, right? Mixture velocity over here, Vs. The gas liquid mixture inside the slug body travel at the speed of Vs, right? So time multiplied by velocity will give me length. Okay. So as the slug body front interface travel by Ls, the particle inside travel by Ls over VTB. This is the time, right? Multiplied by Vs. Good? Meter. You understand this? So it's just the time multiplied by velocity. Okay. So once you finish this example, you should get complete understanding on how slug flow works. Okay. Okay, this is a diagram. T equals to 0, T greater than 0. The front moves faster, but the particle inside, the liquid particle inside moves slower. Question 4. For the moving observer, okay, next to Stuart. Is it Stuart? Okay, Stuart. For the moving observer who travel at the speed of VTB, he or she will see the interface to be stationary, and the liquid inside the slug body travel backward. You get that? Okay. So for front interface, question? Front move at the speed of VTB. Okay. That's how fast the front move. If we have the observer travel with the front, so the observer will see the front doesn't move, right? Make sense? Stuart, come here. The next to you, what was your name? Rico, come here too. Yeah, come here at the same speed and look at each other. Yeah, come here. Walk at the same speed, and you look at each other. Walk at the same speed. To here. Yeah. Do you see him as stationary with respect to you? Correct? Yeah. So if stay, you will have to work more. So when the moving observer move with the slug front, the observer sees the front to be stationary. Correct? Okay. Let's say Stuart is an observer with the front, and Rico is the particle inside. The particle inside will move forward me at the lower speed, and the front move forward me at faster speed. Move. Faster speed. Okay, Rico, you move slow, a little bit slower. What do you see, Rico? Does it appear as if he moving backward with respect to you? Two of you go back over there. Quickly. It's okay, we can do it next time. Okay, now Stuart, you come here quicker, and Rico come here a little bit slower. Look at him. Yeah, when you come here quick. Does it appear to you like as if he moved backward respect to you? Yes? Yeah, when you look at him, you are moving observer. Yeah, Rico seems to move slower, move backward. So if we put, thank you, but please stay. So if we put the moving observer at the speed of VTB, he or she will see the interface to be stationary, and the slug body travel backward at what speed? So it will be relative velocity. So Stuart velocity is VTB, and Rico velocity is Vs. So Stuart will see Rico move backward at the relative velocity, which is VTB, or you have to go back so that you can write it down. Please go back. So it will be VTB minus Vs. Right? So thank you, both of you. So Stuart will see Rico move backward at the difference of those speeds. Okay. That moving observer in question 4 will see the liquid inside the film travel backward at the speed of what? So moving observer move at the speed of VTB. We'll see the liquid inside the film. Liquid inside the film travel at the speed of VRTB. So moving observer will see the film move backward at the speed of VTB minus VLTB. VTB minus VLTB. Question 6. The moving observer will see the particle travel shown in page 1 as the particle moving backward from one front of the slug to another front of the next slug. The time required for both particle for the particle to move through the slug body for the moving observer is what? The time required for the moving observer will be what? Is it going to be length divided by speed, right? Length divided by speed is time. So the length that it travel for the moving observer is Ls, isn't it? The moving observer will see the particle travel from one front of the slug to another front of the slug. So moving observer see the front to be stationary and it looks as if the particle moved backward, right? So I am the moving observer. The particle moves slower. It moved from the one front of the slug to another front of the let's do some correction. For the particle to moving backward from one front of the slug to the end of the slug. So when it moves from the front of the slug to the end of the slug, the distance that it travel is Ls, right? And it travel at the that speed, relative speed, which is VTB minus Vs. Good. Moving observer will see the particle move through the slug body from the front to the back. So moving observer will see the solid particle travel by the distance of Ls. When that happens, it takes how much time? So it's the length, which is Ls, divided by the speed, which is the relative velocity. So it's divided by Ls over VTB minus Vs. Okay. Question. So for number 7, the time required for the particle to move through the film for the moving observer will be L film divided by VTB minus V film, which is V LTB bar, right? So for the moving observer, got this? So the amount of time that particle move through the film. So the moving observer will see the particle to move Ls, right? The distance that the moving observer see, it move Ls. That's the distance. And the velocity is, the velocity of that particle with respect to the moving observer is VTB minus VLTB. Good? So length divided by velocity equal to time. Number 8. Okay. Solomon, for the stationary observer with respect to pipe, he or she will see that particle take s seconds to travel inside the slug body. This amount of time is the same, longer or shorter than the time experienced by the moving observer. So stationary observer who stick with the pipe will see something happen. Is that event will take longer time, shorter time, or the same duration of time? Soliman. Rico. It has to be the same. So when I drop this pen, if I move and I drop this pen again, do I see the pen drop faster than usual? No, you see the same thing, right? So if I drop the pen, it may take 1 second for me. If you run, this pen still take 1 second to drop. Make sense? Unless you move close to the speed of light, but we never reach that point. So the time that everyone seems to be the same. So the stationary, it's time's up. Okay. Let me finish this one and we leave question 9 for you to see the solution. For the stationary observer, if you see the same thing that moving observer see, so that particle will take how many seconds travel inside the slug body? Slug body has a length of ls, right? And the speed will be vtb minus vs. Good. So they will experience the same amount of time. Okay. And Lnet, you want to go over it or you want to see it? So we have time that is travel in the slug body, Ls over V minus Vs. That is the time, right? That is travel in the slug body, and we multiply by the velocity. When actual velocity of particle, so actual velocity of the particle will be Vs plus the time is Lf divided by Vtb minus Vf multiplied by actual velocity inside the film, Vltb. Okay, so this is become Lnet, or the amount of distance that this particle travel forward. Good. We will review this a little bit more next time because today is time's up. But please submit that, and you get 10. Oh, you're not done? After you copy that, you get 10 and you can go. Submit it before you leave this room. If you go out that side, just leave it on this table. Okay? If you go out that way, leave it on another table. And you may just submit it with me.